Good morning, everyone. Come on in. Anyone have any questions while we're waiting? It's like I'm 15 people in class already, so that's good. No questiones? I think that's actual Spanish. I'm horrible at foreign languages. Not making fun of them by any stretch of the imagination. Just making fun of myself and my inability to speak them. I used to make fun of myself by putting ones and stuff like that on the ends of all my words and act like I was speaking Spanish. Students thought I was an idiot. It was great. I actually got corrected one time and I was actually right. I just finally found out I was right. And there's people that were trying to hire a new foreign language teacher were wrong. I said, Sprechen Sie Deutsch? And he said, that's not German. I was like, I'm pretty sure it is. But I felt like an idiot. And then I looked it up and I was right. They were wrong. Nah. All right. Well, it looks like we got enough people in and no one has any questions. Can y'all, it seems like y'all can hear me, but has anybody tried to talk? Because I can't hear anyone so far.
Yeah, we can hear you.
Good deal. Thanks for answering on that. All right, so last time we were into chapter 44, which was on astrophysics and cosmology, and we'd basically gotten up to the point where Copernicus offers a heliocentric model of the solar system, which to them was the universe, because the solar system included the universe included what we know of as a solar system, plus on the order of maybe 10,000 stars. It was, no electricity back then, so you could see a lot of the stars. But oddly enough, as I mentioned before, the stars that you see without a telescope are pretty much all just stars in our galaxy. And the vast majority that you see, even with a small telescope, are all in our own galaxy. So we've got this sort of little 2,000 to 3,000 light year radius sphere centered on us, and that's about all the stars we see. And in our galaxy, which is this giant spiral galaxy, so it has these arms hanging off of it like this, that's about 100,000 light years across, this way and this way. We're about a little bit more than halfway out at 26,000 light years out, and it's only about 2,000 light years thick, but it's sort of got like a yolk. So if you can imagine trying to crack an egg on water, the egg would actually float and the yolk would sort of be the densest part, and it would make sort of a spherical bubble, and then the egg white would be around the edges like this. So that part's about 2,000 light years thick, and maybe another 2,000 above and below for the top and bottom of this sphere. And then, like I said, it's about 100,000 light years around. We actually orbit around it once every 250 million years, which means our solar system's moving at roughly 200 meters per second. That's pretty fast, but still not as fast as, for instance, planets orbit around our star. So Copernicus had done this, and I tried to explain to you that there's what I call the Copernican Revolution, which is basically him being willing to put us outside of the center of the universe. That's how I differentiate it. So we are not the center of the universe. It's sort of like a test for narcissism. Okay. So when I talk about the Copernican Revolution, I'm talking about we're not the center of everything. We're not necessarily special. And I mean that not in a completely derogatory way, but I mean it more like in a science sense. The laws of physics aren't special right here, and they're something different everywhere else. That's sort of the continuance of that typical t-shirt you see with a giant spiral galaxy diagonally across the shirt like this, and it'll have one little star, and it'll have a little arrow pointing to this insignificant star, and it says you are here. That's a continuance of the Copernican Revolution, letting you see that you're an itty-bitty part in a huge universe. Another one is the tree of life, which is what biology has come up with. Of course, other sciences as well, but mainly biology through evolution. We know now that we all descend from one common ancestor. which, you know, you could actually take that as a metaphor for what, as Genesis as a metaphor for that. We all supposedly came, if you're looking in the book of Genesis, which is also spawned somewhat by the Old Testament, which is also somewhat the Torah. And of course, even the Quran leans somewhat on the Old Testament as well. So all of these Abrahamic religions all sort of believe in a Genesis type story. And that's consistent with a metaphor for basically what we've learned from science. So if you feel like you're often pulled different ways by religion and science, it need not be, but there are some differences. Okay, so it appears to us that we have a overlap in our DNA with everything on the earth. Okay, and the more overlap we have, the closer they are to us in the tree of life. So maybe, you know, there was this creature up here that was sort of reminiscent of an ape-like creature or something like that. Well, that led to this species, but it also led to this species and this one and this one and this one. And then you find out that in fact you're a distant cousin of the orangutan. Okay, it does not mean we descended from orangutans. It means orangutans and us had a great grandfather that we descended from. And it appears that you know, if it was maybe 10 generations back, we would probably have quite a bit of overlap. But if you go back, say, 100,000 generations, we're going to have a lot less overlap on our DNA. And putting that together, looking at the structures that biologists look at to try to see what species are related, you know, they look for things like the shape of the pelvis, or a ridge on the skull, the size of the skull, the relative size of the brain pan, all that stuff. They used all that to sort of see that we might be relatives in some sense. And then when DNA came on board, like, you know, long after Gregor Mendel and long after Darwin, those DNA showed us more or less exactly the same thing that we already knew. So the DNA was completely consistent with evolution. And all that goes back to a single common ancestor. And in some sense, we are therefore cousins with cucumbers. We are cousins with trees. We are cousins with grass. We are cousins with bacteria and fungi, all that stuff. So that's what we mean by the tree of life and having one common ancestor. Is we're in some sense cousins to every living thing on the planet Earth. And the more distant we are, the less of the DNA we have overlapping. So that again is a continuance of the Copernican Revolution. It is saying that we're pretty awesome. I mean, we figured out a lot of stuff, but we're just one itty bitty branch off of a huge tree of life. So that's all the Copernican Revolution. And remember, I do that specifically because Copernicus went to the heliocentric model for sort of all the wrong reasons. In other words, he just said we had lost our way from Aristotle, which is a plea to authority. On the other hand, there's also a scientific revolution that I think was more brought in by Galileo and others, but within astronomy and astrophysics and astrology, that was Galileo. And he was willing to throw away everything that Aristotle taught us because experiment and evidence showed us otherwise. That's the scientific revolution. If we're willing to say there's nothing that we can hold in some sense, and there's always something, by the way, but just if we're willing to at least contend that there should be nothing that we're always going to believe no matter what the evidence tells us, then we're being scientific. And in that sense, that was a scientific revolution. And that is what Galileo did. And that's what future scientists did, and scientists that are the science that's being done right now is that. So for instance, you know, if you look at Carl Sagan's book, Demon Haunted World, Science is a Candle in the Dark, you'll learn a lot of different tidbits of information. Like you'll learn that, you know, phrenology, which is a study of the shape of the skull, and iridology, which is a study of the eyeballs, to determine life traits in both cases, they're not really sciences. They seem like science because they sort of accumulate evidence, but a lot of times they accumulate contradictory evidence, and then you get these diversions where, you know, one iridologist is going to say this is definitely causing A, and then another one say this is absolutely causing not A. So when you have those internal contradictions, it can't be really a science. But if you're willing to consider the evidence for anything, then you're being purely scientific. And nobody really can. We all have our sacred cows, you know. When I was a kid, I really believed that the Globetrotters were really coming close to losing. That's everybody's got a sacred cow, and that's fine. So that's the scientific revolution versus the Copernican revolution. Now we're going to continue on that path. So we've got a heliocentric model of the universe. Galileo comes in and did not invent the telescope. That's a common misconception. A guy by the name of Hans Lippershey or something like that. I think he was the one that actually invented the telescope. And Galileo read about that and then made his own and made it better. And what he really did, him and Thomas Harriot, I believe his name is. He's a scientist in the Roanoke Island colonies. Basically, when we traveled to what is now modern day Manio, he was a scientist on one of those expeditions. And about the same time that Galileo turned his telescope to the stars, this guy turned his telescope to the sun. I mean, to the moon. And he might have even actually beat Galileo to the punch. So that's a kind of neat aspect of history that we're just recently learning. But Galileo did and published it, and of course was in the centralized world, so everybody knew about that first. And he saw a lot of things. One thing he saw was that Venus actually showed all its phases. So it had a new Venus, a crescent Venus. Remember the way the moon phases go is when the moon is between us and the sun, the illuminated part's on the opposite side of the moon from us, so we don't see it. That's a new moon. Not only that, it's in the same general direction as our sun. So even if it was a little bit visible, it's going to be up at the exact same time as the sun. So it's really going to be hard to see. So we generally do not see the new Venus. I mean, new moon. If you wait a day, or maybe sometimes it takes 2 days, then you'll get a little fingernail clipping on, usually it's on the right-hand side. Okay. Sometimes it's bottom and top, and that's a little harder to figure out, but it's usually on the right-hand side, almost like a book is closed. And we open it with the front cover like this, and the pages inside are illuminating everything out. But if the book was hemispherical, or hemicircular, I should say, or semicircular, if it was semicircular, then what you'd get is a fingernail clipping shape on the right-hand side. And as you opened it, it would become a half circle, and then a half circle with a little bulb on the side that we call gibbous. And then when it was laid flat open, you'd actually have a whole circle. And that's the full moon. And that's the way you can picture it, is with that little book model. And then as you get past the full moon, it starts to close. So you get a gibbous phase again, but now it's on the left side. And then it closes to a half circle, which again, this time it's on the left side, and that's the third quarter. And then it closes to a fingernail clipping. And then you got, of course, a waning crescent. All those after the new moon, after the full moon is waning, and all those after the new moon until the full moon is actually waxing. And now we got a crescent, and then we're back to the new moon. So that's the phases of the moon, and that's exactly what Galileo saw in Venus. And if you remember our drawing for the heliocentric model, we had, well, let me show you here. Our drawing for the geocentric model, I said the heliocentric. Our drawing for the geocentric model was basically that we had the Earth. We imagined a line connecting the center of the Earth to the center of the sun. And then we had the orbit, say, of Venus. And we had a circle on which Venus orbited. So you can see right here, the illuminated half of Venus is that half. So from us, that would look like this. If it was over here, the illuminated half is this. And for us, it would look like that. Right here, it would be a new Venus. Right here, it would be a new Venus. So over here, it's going to be a crescent. Over here, it's going to be a crescent. So you pretty much only see crescents and new. You don't even see gibbous in that model. But what Galileo showed was that you saw, in fact, exactly like I said. So you remember, you're imagining a half circle book, so a book shaped like that. The cover's black and the pages are glowing with radioactivity. Okay, as you start to open it, the cover becomes foreshortened. The pages start to illuminate from the right-hand side. Then you got a first quarter. This is waxing crescent. like croissant. This was new. And then you've got waxing gibbous. Then you got full. Then you got waning gibbous. And then you got third quarter, which you can guess the waxing, or excuse me, the full moon would be called second quarter. That would be acceptable as well. And then you have waning crescent. So these are the phases that the moon shows. And when he sees Venus having that, then he realizes this model is not going to work. Right. So that was his smoking gun, that the heliocentric, or excuse me, that the geocentric model was crap. Now, as I told you before, Brahe, that strange Russell Brand type character, he actually had a model that was just like the geocentric model, only you take the sun out. So you take the sun and you stick it over here. And then you have everything else doing exactly the same thing with these epicycles and deferents, only the center of the Earth is orbiting the center of the sun. So that was Brahe's crazy model. That would be the Earth and all these things orbiting it, but it orbiting the sun. Okay, so that's Brahe's crazy model. And then Copernicus's model was basically the sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, all in circles. I think I just put two P's in there by mistake. Okay, all circles, constant speed. So it's getting back to Aristotle's teachings that the heavens were immutable, they can't change, ergo the speeds are constant, and there's only perfection in the heavens, ergo you can only have circles and spheres in the heavens. So that was the Copernicus model. Ultimately, like I said, Kepler has an idea of his own. He takes this model and he realizes that the number of planets we have is exactly right to fit the number of perfect solids that exist between the various planets and the sun. So he builds a model on that and sends it out all over the world, so everybody knows. One of the people he sends it to is Tycho Brahe, and that's this guy. He's a Dane, and he owns an island called Hven. And I just looked it up last night. It's really cool. It's right in between like Sweden, Denmark, and Poland. So you can sort of see it all in that little area of the water, and it's actually up in a little tributary that goes up, juts up into the that peninsula. That what do they call the general name of that peninsula with Norway and Sweden? Finland or something like that. But anyways, it's a cool little island in there, and he was given that, and he was the landlord, and he horribly mistreated people. Basically he just kicked them out no matter what. He would raise the rent whenever he wanted to get, more stuff for his lab, all that good stuff. But like I said, he was sort of a Russell Brand character. Russell Brand, the guy that married Katy Perry. Did I tell you the interesting stories about Brahe yet? I don't think I did by my notes. Okay, well, I'm going to go as if I didn't. If y'all have already heard this, please stop me, because the written word that I kept on my notes isn't necessarily telling me all the things I said. So Brahe comes along, and he is the greatest astronomer by that time. And in fact, he, without the aid of a telescope, because it hadn't been invented yet, he was able to build a laboratory where he could get measurements that usually takes grad students a couple semesters before they get good enough to do it, even with modern technology. So it's really impressive what he did. And it's mostly giant protractors with sighting tubes mounted to walls. So that's what Brahe's using. And the walls that he used, of course, can move. And then he's got a hole in the opposite wall so he can look at the stars and stuff like that. So he's able to get really, really precise data. Kepler, who's a really odd bug too, the poor guy, he's nearsighted, so he can't really be a decent astronomer. He has piles. He gets rickets at one time. He's got bad health. He's constantly having to go back and forth to save his mother, because as the times would have it, that once a woman loses her husband, she becomes a widower, and once she loses her teeth, she looks creepy to men, so men will often accuse her of being a witch. And he literally had to go back several times to defend her and keep her from being killed, because people thought she was a witch. So it was really a bad scenario. He practiced sort of medicine, but he was mostly a teacher, and he was a bad, horrible teacher, not unlike me. I'm talking to you about something and I go on a tangent about, Brahe's teeth or something. But he was literally like sitting with his elementary school age kids, and realizes that he's teaching them the perfect solids, and realizes that the perfect solids are just the right number to fit between the sun and Mercury, between Mercury and Venus, between Venus and Earth, and all that good stuff. So he just, like, in the middle of class, starts deriving stuff. So that's the kind of teacher you can picture him as. But he writes that letter, sends it to Brahe, and Brahe is an interesting character too. Brahe, for instance, when he was in college, challenged a man to a duel over who was a better mathematician, and in so doing, he lost his nose in the sword fight. So literally, he had his nose cut off in a sword fight over math. He had a prosthetic silver and gold nose that he would stick to his face with wax, basically, and that's how he, lived his day in and day out without grossing people out with that ginormous hole in his face. But like I said, he was sort of Russell Brand, again, the former husband of Katy Perry. Get him to the Greek, that guy, or also Forgetting Sarah Marshall, that guy. Just a wild guy. And that's basically was Brahe's life. He was nobility, and he partied all day. So like his day would start maybe at 1 or 2 in the afternoon. He'd wake up and start partying, drink and eat, and have lascivious women around, all that good stuff. He had a pet human, what we would call a little person, or what people used to call the horrible word midget. So he had literally had one of those that was his sort of personal jester that he treated more or less like a slave. It was horrible. He had a pet monkey. That's kind of cool. But he also brought a deer into his castle and got him drunk, and then the poor deer fell down the steps and broke his neck and died. So he's sort of a person of the times, but that is a horrible person from our perspective, because we recognize animals as having lives, and that hurts our feelings to think about that. But anyways, that's how his life goes. And in fact, he's such a noble. I don't know if you know this, but nobility doesn't pee or poop. Evidently, it just disappears over time. Of course, that's a complete lie, but that's what they want you to believe. And that's what he wanted his guests to believe at his party. So one day he sat at a party so long and drank so much and ate so much that his bladder exploded. He got septic and died. Not unlike the final death of George Washington, but of course, George Washington was doing something classy at the time, like getting ready to free his slaves. So that was kind of awesome. But anyways, that's how Brahe died. Brahe gets this letter from Kepler and sees, well, this guy's a really brilliant mathematician, and I'm good, but I need somebody that can work in my crazy model, right? So he offers him a job. Kepler, who is more like the modern day Mike Pence. Okay, so imagine, straight-laced conservative guy, probably, prays 6 or 7 times a day like he should, will not be left in a room alone with a woman other than his wife, stuff like that. So he's very, very straight-laced kind of dude. And you can imagine if Mike Pence lived with Russell Brand for any period of time, that would not be a good situation. So that you give you some idea how miserable it was for poor Kepler. So, and by the way, yesterday or Monday's notes, I went and added another page to it. So make sure you got the recent copy, because I'll put all these names somewhat in order on the second page, so you can, in case you forget the names or something like that, you can see them. And I added a couple, so definitely check out that from Monday. I won't put it on this one again, but it is on the Monday one. So this Johannes Kepler guy, comes in, lives with them a little while, doesn't really get the data as quickly as he'd like, so he can't get his work done. And that's probably because he realized he was brilliant and might steal his thunder. So then he finally, well, I say finally, then poor Brahe dies in that horrible case, and Kepler tries to get the data, and the family tries to stop it because they're afraid it's going to, steal Brahe's thunder, which it sort of did. I mean, most people have heard of Kepler, and very few people have heard of Tycho Brahe, which I think is a more proper pronunciation, but I call him Tycho Brahe. But anyways, he went to the courts. They finally let him have it. And to his credit, when he wrote his monumental text, he dedicated it to Brahe. So he really knew at the end of the day that Brahe was brilliant at what he did, and he respected his talents. He just didn't like his personality, and that's understandable. But of course, he came up with Kepler's laws, which y'all learned about in the gravity chapter. So the planets orbit in a heliocentric model like this, only the orbits are ellipses. That's sort of a bastardized circle, and that would have Copernicus and Aristotle rolling over in their grave. And the sun was at one foci, or one focus of the ellipse. Then the second one was that they sweep out equal areas in equal times, which meant they sped up when they were closest to the sun and slowed down when they were farthest from the sun. That too would have Copernicus and Aristotle rolling over in their grave. And then the third was the square of the periods proportional to the cube of the semi-major axis. Of course, that was more or less completely correct. The only thing it missed is the fact that Mercury, due to some perturbative forces, actually causes the line that connects the center of it to the point at which it has nearest approach for Mercury. That line precesses, it moves at a rate of a few arc seconds per century. And Newton's laws can be used to explain that, but they're off by about a factor of 2. Whereas when general relativity came online, that was the first thing Einstein calculated to get some evidence as to his theory being correct, or his hypothesis at that point being correct. And he found that he could actually predict exactly the precession of the perihelion of Mercury. So that was one of the big tests for Einstein's general theory of relativity. So we get Kepler, then Newton comes along. Newton explains it all and says, not only are Kepler's laws right, but here's why they're right. The elliptical orbit happens to be a fact because the force of gravity is 1 over r squared, and there's only 2 forces in nature that can make stable orbits. One is the Hooke's law, F equals kx, and the other one is the gravitational law, which is proportional to r squared. And both of those create conic sections as orbits. So that means ellipses, circles, hyperbolas, and parabolas are all potential quote unquote orbits. Of course, you don't picture a hyperbola or a parabola as an orbit, but it's a way that something can come near a central massive body like the sun and then split away and escape forever. So that was a big undertaking for Newton, and science was on its way, right? So we put together how our quote unquote universe was said to be. But by the late 1800s, we were starting to map out the entire quote unquote universe, and their picture of the universe by the early 1900s or late 1800s. Several astronomers had sort of put together an image of the universe, which was more or less flat, but it had some sphericalness to it, like this. And it maybe was on the order of, I don't know, 50,000 light years. Actually, no, it's more like 10,000 light years across. Now, what is a light year? Well, a light year is a unit of distance, and distance equals velocity times time. So you take the velocity of the speed of light, which I've written exactly here. You take 299, 792, 458, 458 meters per second, and you multiply it by the number of years in a second, which I've worked out here. There's 365.2422 days and 24 hours in a day and 3,600 seconds. So you multiply that by 3.1557 times 10 to the 7th seconds, and you get a nice, neat figure. By the way, here's a neat approximation that will help you. Obviously, the speed of light is either 3.00, so that's 3 sig figs, or 2.998 So 4 sig figs times 10 to the 8. And the speed of light is approximately pi times 10 to the 7th. Notice pi would be 3.14. This is 3.16 really. So it's still pretty close. So that's a nice little approximation that you can use. So I'll do 299,792,458 times 365.2422 times 24 times 36. Oh, times 100. That's 3,600. And I get 9.46. Same answer basically that your book gets, which I'll show you is like on the 3rd page of the chapter. There you go. Yeah, 9.44, 9.46 times 10 to the 15th. Meters, or if you wanted to put it in kilometers, it would be times 10 to the 12th kilometers. So that's a distance that we now use, but you can use other ones. For instance, the distance between the Earth and the Moon is 1.28 light seconds. So Earth to Moon is 1.28 light seconds. Similarly, you can figure out the distance from the Earth to the Sun. That's like a little over 8 minutes. I think your book tells it 8.3 light minutes. And Pluto's on the order of 4 hours away from the Sun. So that's a common unit of distance we use in astrophysics and astronomy and cosmology. But in cosmology, you're normally using mega light years or something called a parsec, which those of you who are Star Wars fans know that George Lucas got that wrong when he was talking about doing the Castle Run in 3.4 parsecs. That was a careless mistake because he didn't realize a parsec was a unit of distance, not a unit of time. But the parsec is basically the distance away from our solar system, or in general, the distance a star is away from our solar system if the star shows an angle of parallax equal to 1 arc second. So that's what a parsec is, and it's about 3.26 light years. 1 parsec is about 3.26 light years. Okay, what do we mean by that? Well, okay, here's the Sun. Here's the Earth in, say, January, and here's the Earth in, say, June or July, right? If we see this star right here, and it appears to be off in this direction, and then we see this star again over here off in that direction, if we actually were to measure this angle right here, if theta is equal to 1 arc second, so that would be basically a double dash like that, which equals 1 arc second, which is 1/3600th of a degree. If that's the case, then this distance from here to here is 1 parsec. Okay, so the formula actually reads the distance in parsecs is equal to 1 over the parallax angle in arc seconds. So one thing that's 1 parsec away will have 1 arc second. And because you can also say like that. So if the distance is 1 parsec, then 1 over 1 gives you 1, so that's 1 arc second. If the distance, of course, is 100 parsecs, then this would be 100th of an arc second. So that's sort of the measurements that we use in to determine distance. And to be advised, you should be advised that the measurement of distance in astronomy is the hardest thing we do. We've come up with really crazy ways of doing it. This is sort of a straight trigonometry way and super helpful. But we can also, if the things aren't too terribly far away, we can send laser beams like they did in Big Bang Theory. It's like maybe the 10th episode when Penny started dating the appetizers guy. They took them on the roof and they shot a laser beam up to the moon. It bounced off of a set of mirrors and came back. And you know what the speed of light is, so you can use distance equals velocity times time and figure out how far the moon is away from the Earth, and very accurately so. Well, you can do that kind of stuff, usually somewhat across most of the solar system, but that's not good enough if you're sending off something farther than maybe it might even be the case that you can't really measure the distance from Pluto to here with that method, but you can still use the parallax method for things that are further away, and that's just basically straight trigonometry or geometry. Then they found another way. Basically, you can see that a certain type of star, a Cepheid variable, if you see that's in a galaxy you want to know, then you can use the Cepheid variable and the fact that brightness of a star, which they use either magnitudes, like a first magnitude star is the brightest, second magnitude is the second brightest, on up to sixth magnitude is all you can see if you have perfect lighting and perfect vision. But that brightness is related to luminosity, which is the total star output. So brightness normally has units of watts per square meter, where watts is the luminosity and square meter is the surface area over which it's spread. Then there's luminosity of a star, which we learned about, well, you can learn about in the thermodynamics chapter. The luminosity is equal to some emissivity constant times sigma times the surface area times T to the fourth power. So T would be the temperature of the star's surface. So it turns out that it's also given the symbol L, and what we know is that brightness is equal to the luminosity divided by 4 pi times the distance squared. In other words, if you know the brightness and the luminosity, you can actually solve for the distance, and that's what Hubble did when he used Henrietta Swan Leavitt's discovery. So Henrietta Swan Leavitt had found that Cepheid variables are variable for a very specific reason. So if you look at a plot of their brightness would go like this. And if you measure that period, tau, that tau can give you the actual luminosity. So you can always measure the brightness because that's just the number of, or the energy of the photons hitting your square centimeter of photographic plate or square centimeter of CCD or camera device or whatever. You can always measure that. So you can get that figure. If you find a Cepheid variable, you can get the luminosity, then you can take and solve for the d squared, and that'll get you the distance away. Yes, go ahead. Somebody have a question? Okay, so Henrietta Swan Leavitt's the one discovered that. At the time, though, the data wasn't that good. So Hubble goes out and he's looking at these nebulas. And nebula, I want to say it's Latin, but it might be Greek. But either way, it means cloud. And what it was there's certain things in the sky that you'd see, and they just looked a little unwholesome. Like you look at it and it looked like a little bit of a blur. Right, so it's kind of weird. You don't know what it is. So they named all those things nebulas. Well, the nebulas turned out to not be necessarily clouds. In fact, there's one type called basically a nebula. So in other words, that one got to keep the name. It's an incubator for stars. So this is a cloud of gas and dust, and it emits light. It also has often numerous stars in it being born, some stars that caused it to be born. But for instance, the Great Orion Nebula is an example of that. However, some of them turned out to be clusters. And that would be basically, hundreds of thousands of stars very close together, and they even exceed millions in some cases. So for instance, if you look at Gemini looks like this. You got these two stars, these two that are a little closer together, these two that are a little further apart again, and then it goes off at a right angle and an obtuse angle. Well, beyond that, you also have Leo, which looks like a backwards question mark. Then the body's back here, but I don't necessarily want to obscure my drawing or my equations there. That's Leo. But right in between there, you'll see this and then this. This one is Cancer. This one's Gemini. And this one is Leo. Now, if you look at that one, there's a little blur in here in the middle. That little blur is one of these clusters, and you can look at it with just binoculars, and you will be amazed at how awesome it looks. And then finally, the others turned out to be galaxies. For example, the Andromeda galaxy. Now, Hubble in the 1920s circa 1920, used the new 100-inch telescope which is, by the way, 2.5 meters in LA, that's in Los Angeles, to look at that one, and he found it was a galaxy. Okay, so it went from a nebula to a galaxy on this, because with that big of a telescope, he could see individual stars in it. And what he realized is that this is an island of stars. What he also realized, even though he's wrong, because at this time, Henrietta Swan Leavitt was absolutely right, but her data wasn't that good. So he thought this thing was maybe a couple 100,000 light years away, which is way bigger than they thought our universe was, right? So he thought it was on the order of a couple 100,000. So let's say 300,000 light years away. In actuality, it turns out to be 2.5 times 10 to the 6 light years away. It's 2.5 times 10 to the 6, or 2.5 million light years away. And the neat thing about astronomy is when you're studying astronomy, you're automatically studying history, because even if you look at our sun, you're looking at our sun how it looked 8.3 minutes ago. So if you're looking at the Andromeda galaxy, you're looking at it how it looked 2.5 million years ago. But anyways, he discovered that that was a galaxy, another island of stars, and he knew that because it was too far away to be part of that thing, right? So he reported that, but he also reported that it was moving. And in fact, what he found is that something 100 megaparsecs away would have a velocity away of, say, 250 meters per second. He found that if it was instead another galaxy at 200 megaparsecs away, then V away would have been 500 meters per second. And if it was 300, then it'd be 750. In other words, if you tripled it, you triple the distance. If you quadrupled it, you quadruple the speed. And I said distance last time, sorry. But if you triple the distance, you triple the speed. If you double the distance, you double the speed. If you tentuple the distance, you tentuple the speed. And he also was able to make the conclusion that not only are we seeing that, but if you transported yourself to, say, some other galaxy, they would find the exact same thing happening. Okay. This is actual experimental data, and I'm going out of chronological order, but basically this is experimental data showing that the Big Bang had to have happened. Okay. In other words, there's not a way for us to understand this except via a Big Bang. These galaxies are not moving through space. Space itself is expanding. So Hubble gave evidence that the universe is expanding. And he came up, of course, with Hubble's law, which basically says, well, there's several ways you can write it, but you can basically say velocity versus distance away, and you get a straight line. And your book gives you the figure. I want to say it's 75 kilometers per second per megaparsec or something like that. Let me find the Hubble constant real quick. Different books use different units, and actually the latest experimental data is always subject to change it because it's coming, it's narrowing down to a closer and closer one. Yeah, 71 kilometers per second. So the slope is 71 kilometers per second per megaparsec. So because of that, you can actually see that that's the distance divided by time over a distance. So that's 1 over time, and this is called the Hubble constant. And if you take 1 over the Hubble constant and convert it, that tells you the age of the universe. That is the time, some distance ago, that all the galaxies were on top of each other. And it's on the order of 13 billion years. So that was the first experimental evidence that we had really of the Big Bang. But in the time preceding that, Einstein had published his general theory of relativity. And when he first created it, he saw something that would allow the universe to contract or to expand. And he knew there was no data saying the universe was doing such a thing. And in fact, he believed specifically that the universe was static, that it looked exactly the way it does now for all time, and it will always look the same way. That was his fundamental idea of physics, and it was something that he corrected for by putting in something called the gravitational constant. So Einstein included the gravitational constant. Which is given that symbol. It's an uppercase lambda. So he put that in sort of as a fudge factor to make the universe static. Well, later comes Alexander Friedman in Russia, but they're going through some crap right now, so nobody gets to get any information from them. They're having a revolution, right? This was around 1900s. 1915 was when Einstein did his paper on relativity. And I call it GR. So when you see GR, that just means general relativity. So Alexander Friedman and also Georges, Georges Lemaitre, a Belgian priest. And also a theoretical physicist. He taught, of course, for the church and was a devout church member. But Georges Lemaitre was the first one to actually show for us to see, because Friedman probably did it about the same time, maybe even a little earlier, but because of where he was, we didn't see it till sometimes later. But Georges Lemaitre analyzed GR and found that it was predicting a Big Bang. GR predicts Big Bang. And the name Big Bang wasn't around yet. That's actually a name that was made up by Fred Hoyle. And he was a person that didn't believe in Big Bang. He believed in a static universe like Einstein. And he was fighting and trying to make fun of it. But Georges Lemaitre made this prediction from Einstein's equation and sent it to Einstein and said, "What do you think?" Well, Einstein said, "Well, your math is correct, but your physics is abominable." In other words, yeah, mathematically, that's what my equations say. But my understanding of physics is that the universe is static, so you're not a good physicist, which was dead wrong. He was just wrong, right? And he said that was the biggest blunder of his life, was introducing this cosmological constant. I called it a gravitational constant earlier. It's cosmological constant. He said that was the greatest mistake of his life. And he said he had picked on experts so much that this was his punishment. God made him an expert, and then he screwed up. So that was another kind of way of looking at it. So Georges Lemaitre made this prediction. Alexander Friedman made this prediction. Then some students of George Gamow had a student named Ralph Alpher, who died within the last 10 years. And another student was named Robert Herman. Most of the work was done by Ralph Alpher, but Robert Herman did some credit, to his credit, did some work too. But anyways, Ralph Alpher took this idea and ran with it. George Gamow said, hey, why don't you go see what you can predict about the Big Bang if it existed? Well, what he did was he took the percentages of hydrogen and helium in existence and then was able to predict the percentages of lithium, beryllium, boron, which I think is just B, by the way. But anyways, he was able to predict these concentrations. He was also able to predict rate of expansion. And he was also able to predict microwave background radiation. In other words, a radiation that would be coming from everywhere. And it should act like something that has a temperature on the order of 2.7 Kelvin. I think he said like 3 Kelvin. And when we found it was like 2.7. So it was really brilliant that he predicted this. And what it is after the Big Bang, the energy is so high because of the smallness of the universe. By the way, the universe means all the matter, all the energy, and all the space itself, including the dark matter and dark energy. That was all created. And according to that, initially it was to be so energetic that you only had like fundamental particles and energy. But slowly those fundamental particles would come to fruition and make, for instance, hadrons. And once you had hadrons, of course, you could start building baryons and mesons, or the different parts of the hadrons. You could make atoms. Once you start getting particles coming together, then they're not free to absorb all the radiation around. They have very select radiations they can actually see, or they can actually absorb, and everything else goes through. So initially, the universe is completely opaque for about the first 380,000 years. Then when these particles start grouping together, they only have certain energies they can accept. So at that instant in time, there was a ginormous amount of light that shot out, and that's what this is. It's a radiation that shot out from all that initial stuff about 380,000 years after the Big Bang, and therefore it's around. But the universe has expanded so much, it stretched its wavelength to match a 2.7 Kelvin temperature. So I think that's enough for right now. We've run out of time. It's actually a little bit after, but we'll finish this off next time. And I think you have a pretty good understanding of what's going on. This is all in your book in somewhat of a different order, but it's really amazing. Poor Ralph Alpher did all these predictions and got nothing. The guys that learned that someone was looking for this radiation hadn't heard of their paper, but they had already found it, and they win the Nobel Prize. Ralph Alpher never got it, and he really should have. I mean, a grad student for a PhD actually predicted the existence of the background radiation, and they don't give it to him, but they do give it to the guys that showed it existed. So kind of a bummer, but you guys are free to go. I'll wait for the last one to leave. Remember, our labs this week are only review sessions, and they're optional. And those of you who had me today, I'll see you at 1 o'clock. Kayleen, Elizabeth, Brandon, y'all have any questions? All right, I'm going to call it. See you, everybody.